Yeah, so CMC has faculty housing for us. It's just you know where the big gym is. It's all those houses south of that is CMC housing. So I know like 80% of those houses are owned by CMC, and then there's just random other people living there. Okay, today. Well, maybe before we get to this week, lots of things going on this week. My, well, I mean, I guess it may feel like a lot of things going on this week. It's really the same amount of normal things going on this week, though. We have 2 assignments due tomorrow. The Padilla number 3 assignment, which was just our weekly assignment, and then the Twitter assignment is, which was given, I don't know, a long time ago now, is finally going to be due this Tuesday. Then we'll have the quiz on Wednesday, which is about the space that the rows take up when you insert and the various overhead caused by that. And then after the quiz, we'll post the midterm, and you will have until Sunday night to complete the midterm. A couple of people have asked me for individual extensions to the end of spring break, and I'm happy to do that on a one-by-one sort of basis. I don't want to just generally make it to the end of spring break, though, because my goal, at least for this class, is that you all not have anything at all that you have to think about over spring break. So I don't want you to be tempted to put off the midterm until the end of spring break. Really, you should try to do it before Friday, and I'm just making it due on that first Sunday because I'm definitely not looking at them before Monday. So there's no point in having an artificial due date. Any questions about? Yes.
I have a question about here.
Sure.
The command to look at the bytes that like each data takes, do you have to be in, can you be in any PCSQL environment to get that table, or do you have to be specifically the one that give it to us for when you did that?
Yeah, so the questions about so I'm going to take us to the last week's notes here. There's a command listed here. This command right here, this is the one you're talking about. And this is what you run in order to know what is the size of a particular type. And the question is, do you have to be in the SQL quiz environment to run this command, or does this work anywhere? And the answer is that this works anywhere. There's a number of tables that are sort of built into Postgres that have this PG underscore in front of them. And these tables, they're always available. It actually turns out if you want to like create your own data types in Postgres, which is something that people do quite frequently, the way you do that is you just do that by inserting a row into this table, and that creates a new data type. So this command right here can be run from any environment. It's possible that you'll get additional results if you ran it in a different environment, but the SQL quiz environment doesn't extend this beyond the defaults. So any other environment that you ran it in, you would only get a possible superset of the things that you would get in SQL quiz. Does that answer your question? Cool. Good question. And I'll also say that this is one of the advantages, I guess, from like a theoretical perspective about like, I don't know, maybe from like a beauty aspect about Postgres, about why people like it and it's nice to work with, is that anytime you're trying to extend it or find out information about things, you can do that just inside of SQL commands. The other databases, they're not, or the information about data types, for example, is not just stored as a SQL relation. And so you have to do special things to get access to that. But it's kind of nice that Postgres, they managed to design things so that all the information, all the metadata about Postgres is still stored in Postgres using normal SQL features? Good question. Any other questions about anything administrative or not administrative? Okay, then today in our topic 7 here, transactions. This week we're going to be talking about things, transactions and locks. And again, we're making this transition away from just having correct SQL to having fast SQL, or more generally, just fast code in general. And how do we do that? The first thing that we're going to be thinking about is that in order for speed of our SQL queries, our select statements to matter, we have to have a lot of data inside of a database. And so we're going to talk about how do we insert a lot of data into a database in an efficient manner. Your next homework assignment is going to involve that Twitter data that was that you used for the MapReduce assignment, actually inserting it into a Postgres database. And you're not going to have to insert all like however many terabytes of the data into Postgres, but you'll have to insert a significant chunk of it. And in order to make that insert go smoothly, you'll have to do it fastly and do it in parallel. And in order to make those parallel inserts actually work, you'll have to understand these transactions and locks that we'll be covering today and this week. This topic is sort of an example of concurrency in programming, and concurrency has the reputation of being by far the hardest computer science concept there is. That anytime there's like weird bugs that only appear like 1 in 1,000 times somebody's using systems, it almost always boils down to concurrency and people doing things with concurrency wrong. And it's incredibly difficult to figure out, to debug those problems. So we're going to not fully dive into that topic and these debugging things, but we will be scratching the surface. And well, yeah, when we get to the technical stuff today, you'll see that it is, there's a lot of technical things going on. We're going to be going over this quizpractice.pdf file right here today. That'll be our main technical thing. This quiz will be for the Wednesday after spring break when we'll have the actual quiz itself. And the format of this quiz will be a little bit different. You will have access to a computer for the quiz. You're going to need to reference the Postgres documentation. That's why you'll have access to a computer. And because of that, I did not print out a whole bunch of copies of this quizpractice.pdf. If you look at the actual, so I have the file pulled up right here, look at the file, there's 24 pages to the practice problems. So there's a lot of practice problems here. It looks like I have one more physical printed copy printed out up here, though, if you would like a physical copy. But otherwise, you're welcome to download the PDF file right here and take notes as we go through it today, directly in the PDF file with whatever annotation software you like to use, because you'll be able to use those electronic notes during the quiz itself. The question is, do we have a SQL quiz this Wednesday? And the answer is yes. Next class period, we will have a quiz on the disk space that individual inserts take up in your tables. If you come back to last week's topic 6 folder, the practice for that is not in here. It is in the SQL quiz repo, and it's the quiz practice 3 right here. This is the practice problems for the Wednesday quiz. The stuff that we'll go over today is not for this week. It is for the week after spring break. Because, well, let's see, there is also going to be a programming assignment that goes along with this. I don't want to give it out yet. I don't want you to be thinking about it, have to think about it over spring break. So give it out after spring break sometime, and it won't be due on Tuesday that week. You'll have plenty of time to work on it. But besides this quiz, there will be some programming stuff that goes along with it. Any other questions? Okay. So these links right here are the things that you'll need to be referencing for the quiz. We'll go over how to use those and talk about the quiz here in a little bit. Before we do that, though, I just want to do some high-level stuff to get us started motivation-wise. This first phrase right here, ACID, is a very common phrase in databases. And the ACID stands for Atomic, Consistent, Isolation, and Durability. And our quiz is going to be talking about these three features: atomicity, consistency, and isolation with databases, and Postgres in particular. You're not going to need to know, like, I don't know, the detailed definitions of each of these terms. But I'll be highlighting them a little bit as we go through the quiz. These are just things that you'll see people throwing around a lot, terms you'll see people throwing around a lot, and they're very highly associated with this idea of transactions and locks that the quiz material is going to be over. This last item down here, durability, this is something that we're not going to talk about at all in this class. It's the basic idea of durability is that if your computer catches on fire, how can you actually recover the data from a totally destroyed computer or a system that is behaving incorrectly? So this is also an extremely difficult and technical low-level programming thing. It doesn't impact user interface at all. These things up here will impact the user interface, and that's what we'll care about for this course. I've mentioned NoSQL databases a handful of times in this class. This is really the main, one of the main differences between NoSQL databases and SQL databases like Postgres and MySQL and Oracle and SQLite. NoSQL databases are typically not ACID compliant. So not only do they not offer you the ability to join relations together, they do not offer this atomic, consistent, and isolation guarantees. MongoDB is probably the most famous of these NoSQL databases, and they are also infamous for misrepresenting themselves as having these ACID guarantees when they in fact don't. There's this famous company called Jepsen Analysis, which analyzes databases, trying to find bugs inside of databases that cause various corruption. And Jepsen found dozens of ways where MongoDB can accidentally drop data or corrupt their database. And MongoDB still insists that they do have these things when all the actual database people say that they don't. So they have a very good marketing team about that. If you want to read details, there's details about all the drama, a very dramatic thing for the database world. I have two more practical links down here. So there was a social network in the 2010s called Diaspora that used MongoDB in the back end, and they ended up having to shut down because their social network got corrupted because they were relying on the ACID guarantees of MongoDB, and it failed them. If you want to read about that instance, there's a link there. And famously, The Guardian, so the famous British newspaper, used to use MongoDB to store all of their news articles on their website. But then they suddenly realized that their news articles were disappearing and they didn't know why. And it turned out to be because of MongoDB not supporting the ACID guarantees that they were depending on and just randomly dropping their data. The reason people use MongoDB is because it's very, very fast at different things, but it's fast because it drops your data when it is inconvenient for it to save your data. And it also turns out that Postgres, if you want it to have the same guarantees as MongoDB, you can disable all of the ACID compliance things. You don't need to look at any of these documentations here, but this is techniques on how to disable that if you want in order to get the same speed. But you never want to do that in practice because you're probably saving your data because you actually care about your data and don't want it to disappear. We're going to go into the actual technical stuff here next. Any questions about anything, the high level things before we get into the technical quiz material? Okay, so I have opened up here the quiz and two terminal sessions over here. I apologize that the quiz, I can't zoom it in any further than this without, I'm just trying to keep a lot of stuff on the page at once here. But hopefully, if you can't read what's on the screen, you can just pull up the PDF file on your laptop and zoom in to be able to see a little bit better there. I have the main purpose of transactions and locks is so that you can understand the semantics of how multiple programs using the database at the same time will work together and how they will be able to share data together effectively. For the purposes of this quiz, we only have two programs that are working together at the same time, that all of the weird edge cases can be recreated with just two sessions. But again, in your future homework assignments, you'll be having many 40 or 80 sessions working together at once, inserting lots of information into a database, building up the database in a fast way. And if you don't design those programs correctly, then they will have lots of problems related to what we're going to talk about. I don't know, with all these quizzes that we do in class, I think of the quizzes as like understanding the how or the what, the mechanics of different things. We're just going to be focusing on the mechanics of these transactions and locks today. And then the programming assignment will focus on like the why you care about all of this. So it's great to ask why questions if they come up today, but really focusing on the how and the what. In each of these problems, I have two columns, session 1 and session 2. And these two columns correspond to my two terminal sessions over here. In these terminal sessions, let's just real quickly run Docker PS. I have a Postgres system running right now. I'll go ahead and just make sure we're in a sane state. I'll bring it down first and then up again. Let's Control C. I need to do up-D, so it's a daemon, so I can connect to it. And I'll do Control R, find my psql command, docker compose exec pg psql like this. And then down here in the bottom, that's crazy commands. Also connect with psql. So I have these two terminal sessions opened up to the same database at the same time. And what's going on in these two systems, or in each of these problems, is each line, each of these numbered horizontal lines, you'll see only has a single command in one session. So like this line 1 right here, this row 1 has a command in session 1, but not a command in session 2. That means that this command right here gets typed up in the top box. That'll be my session 1. And then so that'll be create table ta int like that. And then after that is completed, we will go on to line 2 down here, and this command will run in session 2. And so here it says select count star from T down here, select count star from T. And we haven't inserted anything into T yet, so we should expect that that gives us nothing as an output. And that'll give us nothing as output no matter which of these two sessions we run from. So I'll just add that up here, and we get nothing as output in either location. If I insert things in session 1 on the left-hand side, so line 3 says insert into T values 5 like this. And then line 4, press the up arrow to change that 5 to a 6. We've inserted things now, 5 and 6, into this table. And we can view those values that we've inserted from any Postgres connection, whether it's the top one or the bottom one. So in the bottom, if I now rerun the select count star from T, we can see that there's 2 things inside this table because I inserted 2 things in this session up here. And if I insert one more thing up here, so this line 6, inserting a value of 2 up here. Then down here, I can rerun that and we'll get a 3 down here. So the main idea so far is just that these commands get ordered according to their, you can think of these rows as like time, that the top is the start time, and then each time value is a single command that gets run, and you'll always have exactly, or you'll only have a command in one session at a time and not a command in both sessions. For the purposes of the actual quiz, the thing that you need to do for this first problem, a problem like this first problem, is there's going to be 4 different things that you'll have to be annotating on these problems. But the only thing that is important at this point is this part 4 right here, where it says write the output of each select statement. There are 3 select statements over here. And so for the quiz, you would have to write something like this first one had 0 things inside of it. The second one had 2 things inside of it. And this third one had 3 things inside of it, like that. So we haven't done any of the interesting stuff yet. This is just describing the problem setup. But are there any questions about what's going on in the problem setup or anything?
Could you be able to run a command to show us the values in the table? Or like if we wanted to do these values in it?
You're saying, so we have the table T here. How do we see what's inside the table T? So right now I'm doing select count star from T, so that's showing me the number of rows. If I just do select star from T, that'll show me the contents of it, 562. Okay. And the key thing here is that it doesn't matter like where we're running it from. We're going to get the exact same results here in both sessions. Soon we will see weird things where these 2 sessions will not have the same exact results, and prepare for your brain to break. Yes, Nico. Yeah, so this this first one right here is, there's nothing interesting going on. It's just to get us the hang of the problem setup for the future things. Yeah. So yeah, here this table that we created, T right here, has no restrictions on it for this A column. It can be null or not null. So if I inserted a null value, then down here you can see the null value was added right here, and changing that to a count star like that still counts the null rows. So I could change this count command to something like count A. And then again, this only counts the non-null rows if you put a specific column here. I thought about, for this quiz, combining these weird SQL features with the transactions and lock stuffs, but I decided not to do that. So all of the like SQL select statements and SQL syntax will all be very, very straightforward things. The weird stuff's just going to happen with like their ordering about things. Okay, so problem number 2 here gets us to the first weird thing that's going on. Before we get to problem number 2, though, we have to reset our system in order to be able to rerun these commands. That you'll notice here, if I rerun the create table T a int, create table T a int like this in my session 1 right here, if I rerun that command, we'll get this error that relation T already exists. Each of these problems, you should think about it as being in its own separate SQL sessions, where between each problem, I've done Docker compose down, and then Docker compose up dash D again, creating a brand new from scratch database so nothing can affect anything else. And now I can rerun that create table T command, T-A int like this, and it works. That's how you should think of each of these problems. It's kind of a pain in the butt to rerun all that stuff each time, and you don't actually have to do it. All you have to do is, I'm just going to delete the results of the previous problem to go on to the next problem. And so the way that in SQL you delete a table is you say drop table T, and this removes that table. If I do the \D command to list the tables, I get the basket tables because those are part of the just part of the database, but that T table is gone now. So from now on, I'm not going to bring down the database and bring it back up in order to go into another problem. I'm just going to drop the appropriate tables. Problem 2 over here, the key, yes, question. Question is, if you're using Docker and you bring down the containers, do you just lose the database? And the answer is by default, yes. But that's where the volumes come in, that we have the Docker volume and we put our database inside the volume so that we can bring down the database and bring everything down and the data is still saved in the volume. But yeah, so there's a lot of like very subtle configuration issues there that are important. Problem 2 here. The key difference between problem 2 and problem 1 is there's this new syntax of the begin and the commit commands. And the begin command is what starts what's called a transaction in SQL. And so here, I'll press the up arrows to rerun my create table here in session 1. Session 2, we'll do select count star from T like this, 0 as we expect over here. So I'll go ahead and annotate that with there's a 0 right there. And now the begin command up here is beginning a transaction on this session 1. And the key thing about transactions at this point is this I word, isolation. And that's that a transaction that's in process can't interact in any way with any other transaction. If I come back to here, we have a transaction that's in progress in the session 1 over here. And the key idea is that it can't interact in any way with what's going on in session 2. So in session 1, I'm going to insert into T values 5, insert into T values 6 like this. And down here, so I've run steps 4 and 5 now. Step 6 is where I'm at. If I run that, you see that I still get a 0 over here. From sessions 2 perspective, line 6 and line 2, command at 6 and command at 2 see the same information. They see the same information. So this still gets a 0 here because we had a 0 over here as our output. If I'll rerun, so line 7 over here, up arrow, insert the 2, and then we run a commit command right here. Commit says that whatever inserts or whatever changes you've made to the database during your transaction, those are now visible to everybody else. We do that. There's the commit. And now that was line 8 over here in session 1. And now line 9 in session 2, we do another select star, and now we have access to that information. So because these, so there's a 3 right here would be the answer. Because these lines right here are inside of a transaction, and Postgres has this ACID guarantee of isolation between transactions, it means that any query in session 2 that happens in the middle of the transaction doesn't see any intermediate effects of that transaction. Questions about that? Lauren?
If you're to do a select statement in the middle of the transaction, that would show.
Great question. So the question is, here we have select statements on the right-hand side in session 2. What happens if we have select statements on the left-hand side in session 1? So I'll just create that environment right here with a begin. We'll do an insert. I'll start with a select count star from T like this. There's the 3 things at the beginning of our session. I'll do the up arrows to get to an insert like this. To insert a couple of things. So we've inserted 3 more things. Select count star, we have 6 inside of the transaction. This select statement right here is inside of the transaction. But on the right-hand side, we're not inside this transaction. I'm in a transaction here because of this begin keyword up here. So I'm inside of a transaction on the left. If I come down here on the right, on the bottom, and run the select count star, we still only have access to 3 things down here. But then if I type commit, basically save those changes, then I do suddenly have access to 6 down here. Yeah. There's it's how it's implemented under the hood. In like 4 or 5 pages, we'll be talking about locks and stuff explicitly. Yeah. Good questions. Any other questions so far? So this is the isolation property of transactions. There's the atomicity property of transactions is what we'll see next. That the reason why you use transactions is because you might want to start inserting values and then suddenly later decide that you don't actually want to save those values. So that's what problem 3 talks about. And the key idea on problem 3 here is that instead of a commit on the line 8 right here, we have this keyword rollback. So I'm going to drop my table T to get myself back to an empty session. I'm also going to do, I know my screens are a little bit cluttered right now. I don't like that. In Postgres, if you use \bang like this, you can run terminal commands. The terminal command reset will clear your screen, and you see my terminal is set up so that it also rearranges the vertical bar so there's no scroll history anymore. So let's do a \bang down here, reset, get us a nice blank problem section, and we'll do problem 3 now. So create table T a int, and then down here select count star from T 0 up here, begin my transaction, insert into T values 5, values 6, rerun the select count star. We're still in the transaction, so nothing happens. Up here, let's add another insert 2. And so I've done everything from lines 1 up to line 7 now. And the key difference between problem 3 and problem 2 is line 8, where we have the rollback. And so now if I type rollback right here, then this is like undo everything. And we're no longer in the transaction up here. But now the select count star, no matter where it gets run from, doesn't see anything. So the rollback says all the changes that were made between those begin and the rollback, they get forgotten about. And there's no way to recover any of this data from any other session. The rollback and the abort, rollback and abort are synonyms of each other. Aborting a session is 100% identical to rolling back a session. Any questions? Yes. Question is, what happens if you commit before you roll back? The answer is that, so let's just see what happens. Let's begin. Let's insert a single value. Let's do a rollback. Oops, sorry, your question was commit before rollback. So begin, insert, and then commit here. That saves everything like this. And now if I do rollback like this, we get an error saying there's no transaction process. That begin is how you always start a transaction. The begin always starts the transaction. Transaction sometimes abbreviated just TX, and rollback or commit or abort will end the transaction. So the fact that I did the commit already means that I'm not in a transaction anymore. And so the rollback doesn't make sense because there was no begin that corresponds to that rollback.
So like after you go back to it, just
So the question is, after you roll back, can you do you have to start with begin again? And the answer is that after you do rollback, if you want a new transaction, you have to run begin again. But you don't have to be in a transaction to do an insert. So right now I'm not in a transaction over here. I know I'm not in a transaction, for example, because I just tried to run the rollback command and it tells me there's no transaction in progress, but it's perfectly okay for me to do an insert like this. Technically, in SQL, this is what's called an implicit transaction. It's an implicit transaction because we did not use the explicit begin and commit commands. But an implicit transaction, the implementation of insert like this is 100. This command is 100% equivalent to begin, insert, and then commit like this. And that's actually how it's implemented under the hood, is that this is just short, like syntactic sugar for this. Yeah.
And then you do instant transaction log.
Sorry, say that again.
So you said instant. And then when you do that,
When I restart a transaction?
how do you explicitly show the
I see. So the question is here on line 3, I have an explicit transaction, and then line 4, I have this insert command right here. And I just said that insert is syntactic sugar for this. So there's like a transaction inside of a transaction. It turns out that nested transactions are perfectly valid inside of Postgres. They have extra weird edge cases, which we're not going to talk about. You're not responsible for knowing anything about nested transactions. But one of the advantages of Postgres over some other relational databases is that it does have full support for nested transactions. And yeah, it basically does what you expect that it would do, that you can abort a nested transaction without aborting a full transaction, but there's extra weird edge cases stuff that we won't talk about. Okay. So that's all for the basic transactions. What we're going to talk about next are isolation levels. So Postgres offers this isolation guarantee, and it turns out that there are 4 different guarantees that the SQL standard demands that a SQL database can provide. And Postgres supports all of those. If you come over to the notes here under the quiz, it looks like I have a markdown typo right here, but this is the documentation that you'll be expected to reference for this. And these are the 4 different transaction levels. You're going to be responsible for this read uncommitted, read committed, and repeatable read isolation levels. You'll not be responsible for the serialization ISO level, which is basically the same as this repeatable read, but different in ways that can't be tested in this testing format. So that's why you're not responsible for it at all. The details here, so if you click this link, you'll come up to the Postgres documentation here on the isolation levels. And at the very top of this document, it talks about different types of what are called transaction anomalies here. You're not responsible for understanding the details of any of these transaction anomalies. But reading through it and understanding it can help you understand the differences between these isolation levels. So I recommend giving it a read just to get a sense for those things. This table right here is the technical summary of these different isolation levels, but we'll go over the sort of intuition here in the quiz in these next few problems. By default, the default isolation level is, so every time you have begin by itself, the default isolation level in Postgres is read committed right here. And let's see what happens with our read committed isolation level. I'm going to stop following the, well, maybe I should follow the things exactly so that you can, I'm going to start just by getting myself into a new problem state right here. And let's see what's going to happen here. I'm going to go to, let's do, session 2 right here, session 2, or sorry, problem 6 is what we're going to take a look at. What's going to happen? This is the, so problem 5 right here is the same as, okay, let's just do problem 5. It's the same as what we did, but I don't want us to get too confused. So difference between problem 5 and the previous ones is on session 2 over here, all of these select statements are happening inside of a transaction. So now we have 2 transactions going on. On the left-hand side, we have a transaction for our inserts and a separate transactions for our selects. So session 1, create table T a int like this. And then session 2, begin, semicolon, select count star from T. We get a 0 right here, 0 at this line right here. And then we're on line 4, begin our transaction. Oh man, typo. Begin my transaction, insert into T values 5, values 6. So that's lines 5 and 6 that I just ran. We're on line 7 over here. We know that this count star over here is not going to give me anything. It's going to give me a 0 result, even though I've inserted over here because this is inside of a transaction. And so it's isolated from what's going on over here. So I hit enter, we get a 0. I haven't written it out, but line 3 and line 7 are both zeros over here. And then we're on line 8, inserts the 2 and the commit over here. And now, even though we're in a transaction over here on the right-hand side, line 10 right here, I do this select count star, and we get a 3. We get a 0, 0, 3 right here. Even though all of these select statements have happened inside of the same transaction, because the insert transaction here on the left-hand side, line 9, happened before line 10 in the transaction, we still get a 3 value over here. And we'll commit this transaction now. We haven't made any changes inside of this transaction, so whether we commit or roll back is 100% immaterial. All of these things are selects over here on the right. But now if we do another select count star, we still get a 3 value over here. This is sometimes undesirable behavior, what we have going on over here on the right-hand side. That again, this begin transaction, and anytime you don't specify a transaction level, this is the read committed transaction level. That's the default transaction level. So this is read committed. So we can only read things that have been committed in another transaction. And so at line 10, the commit has happened, and so we're allowed to read from that transaction. Problem 6 is different because now we're not in the read committed, we're in the repeatable read transaction level, repeatable read. And so what's going to happen is here, this will be 0 and 0, just like before. But now what repeatable read ensures is that anytime you run a command, if you run that same command another time, you're guaranteed to get the same results. So because we've already ran a select count star inside of this transaction over here, I'm guaranteed that every select count star is going to give me a 0. And so this is going to give me a 0 over here instead of a 3. I'll commit that, line 13, then I'm outside of the transaction, so no longer have to enforce that consistency. And so we'll get our expected 3 value down here. The key difference about the repeatable read again and the default transaction level is that with repeatable read, when you read from a table, you're guaranteed to always get the same results. And so we get 0 down here because we previously got a 0. Again, the default transaction level is read committed. So this is exactly the same, having all of this code right here. All of that code is exactly the same as just not having it. So this is redundant, not necessary. And so if we ran through this, select count star right here would not have access to any of these inserts. So we'd see a 0 right here. This select count star on line 10 happens after the commit level. We're reading things that have been committed. So we will have a 3 here and then another 3 down here. Any questions about the difference between these isolation levels? Confusing thing happens with the repeatable read isolation level. That's repeatable read does not mean that you're seeing what happened at the very beginning of the transaction. So here, let's go ahead and, well, I don't need to go ahead and run that. It'll be faster just to tell you. It's the very first time that you run the select, you're allowed to look at things that have happened during the changes that have been made during your transaction over here. So this select right here is allowed to look at this information over here in this commit because it's not the very first select statement that's happened. And so this will give you a 3 value right here, and then another corresponding 3 value down here. This is different than the previous repeatable reads because we're not trying to repeat a read at this point. This is our very first read from a table at this point. And so we'll use, at the very first read from a table, we'll use whatever information is currently in that table. The difference between problem 8 and the previous repeatable read problem is that there used to be another select up here that read from the table before this commit happened. And so that one returned a 0. So this one is also forced to return a 0. This implies, and this is a little bit weird. I think I've used this phrase of idempotent commands before, talking about the shell. That's things like ls being idempotent. Normally, we would think of the select operation as being idempotent, but select is not idempotent in SQL. That's running a select query can, in fact, change the results of future select queries. This is a really bizarre behavior and can cause lots of unexpected things in real world programs where you're not having such fine-grained control of what gets run when. Okay, let's jump ahead now. It's enough about the isolation levels. I'll be skipping over a handful of these problems, leaving them for you to work on them and think about them for yourself. And we'll head down next to this explicit locks section. The locking is what allows Postgres to do to have these insert capabilities and maintain the consistency of our database. So this is now going on to the C of our ACID guarantee, the consistency, that we're guaranteed that our data will always be in a valid state. At this point, our data can't be invalid because we don't have any constraints on the columns here, but eventually we'll be adding things like unique constraints and foreign key constraints, and the locks will be a key component in ensuring that that happens well. Here, so the new command here is on line 3, this lock table T in, and then a mode that you're locking the table in. And we're going to see that this is going to, how these locks will interact with the various sessions here. Go ahead and drop my table T so that we can restart from a new session, reset everything here. And I'm on line, problem 10 is what we're going over right now. So create table T a int like this and begin, and then lock table T in exclusive mode like that. There we go. We get this lock table command down here. Now on the right hand side in session 2, I'll do begin like this, and then lock table T in share mode. Lock table T in share mode. And what we're going to see is that this command right here does not give control back to pSQL. That this is what is called a let's make sure I'm using the term I used up here. This is what's called a blocking operation. And so when your command runs like this and it doesn't immediately give control back to pSQL, we say that command has blocked. And so the instructions for this quiz are that you should circle that SQL command. So coming back down, we're on problem 10 right here. It was this command 5 right here that blocked. So circling the line number or circling the command, or just somehow making it clear that this is the thing that blocked is what you should do. This command right here again is blocking because we do not immediately get control back to pSQL. We will get control back to pSQL on this line 5 when this lock on table T from session 1 is released. And the only way that the lock on table T can be released is when the transaction is over. So on the left-hand side, I'll type commit over here. This is going to end the transaction on the session 1 on the left-hand side. And as it ends the transaction on session 1, it will release the lock on table T, which will allow this line right here to continue. And then it will give me back control in pSQL. So I'll hit enter on, you'll notice what's going to happen as soon as I hit enter, that now the lock table T in share mode was allowed to finish its operation, and we get our control back over here in pSQL. And so running the commit operation like that finishes up the transaction. In general, it is very, very rare to use these explicit locks. These are called explicit locks because we're actually using the lock command right here. And the only purpose for having this section on explicit locks is so that we'll be able to understand later on what's happening inside of implicit locks where there is no actual lock command going on. Pause here for questions in just a minute. The last thing for us to talk about is exactly why this command right here, line 5, why it blocked, why it did not run when this line 3 had locked the table. And in particular, if I were to rerun this command up here, line 3, with a different, what's called a different lock level. So in this case, instead of exclusive, we will take share mode like this. So we now are in share mode on the left table. And down here, if I begin and try to also lock in share mode, that's perfectly okay, and we do not block in this case. So share, do not block. The row share also will not block. If I do row share like that, also not blocking. So I'm looking at problem 12 right now. This is a share and a row share right here. These are compatible with each other, so they do not block. So control flow for each of these continues going, and we don't have to wait for the other program to finish. How do you know which lock levels block which other lock levels? If we come over to the Postgres documentation, and here under the quiz details, this is the bottom explicit locking section right here. If you click on that link, you'll come over to this explicit locking web page. You're going to be responsible for understanding the entirety of this documentation page. You don't have to memorize it. Again, you'll be able to have access to this during the quiz. but there's a lot of information on here that you'll have to look up and figure out exactly what's going on for an individual problem. In this case, it's this table down here that we want to investigate in order to determine which locks are going to be compatible with other locks and which cause the table to not block, cause pSQL to not block. The requested lock mode down here, the requested lock mode, this is going to be the lock mode that is on the right-hand side in this case, the lock mode that happens second. And the existing lock mode, this is the lock mode that is happening on the left-hand side, or more importantly, the lock mode that is happening first. So in order to know if line 5 right here is going to block, I'm locking in share mode. So I come over here to the share mode under my requested lock mode. The line that I'm currently executing is share. Line 5 right here is what I'm currently executing is share. So I come over here to share row over here. And then I look up the existing lock mode. The existing lock mode is exclusive because up here it was locked in exclusive mode. And because there's an X in the corresponding X tree in that table, so in the share row, under the exclusive column, there's an X here. That means the command will block. So this command right here blocked, and I would know it was going to block without actually running it because I looked up in the table in the share row in the exclusive column. This command down here did not block because if we look up the row share mode, the row share right here, the row share mode, and look in the share column right here. The share column is the existing column on the left-hand side, the share column right there. There is no X, so the commands are compatible and they do not block each other. So this no blocking in problem 12, yes blocking in problem 10. A lot of things that's covered there. Any questions about any of that? Yeah. Great question. The question is, do you have to be in a transaction to lock a table? And the answer is yes. Let's go ahead and roll back this transaction right here. So we're no longer in a transaction. I'll run that again, just to be clear, we are not in a transaction. And if I type lock table T in, doesn't matter what mode I do, share mode like that, it'll tell us that the lock table can only be used in a transaction lock. If you are using an explicit lock, then the lock is acquired at the line where you use the lock command. And the only way in Postgres to get a lock to be released is to end the transaction. So you have to be inside of a transaction to use a lock because the only way to release a lock is to end the transaction. So the commit command or the rollback command or the abort commands will all end a transaction, all release the appropriate lock, allowing any blocked commands to continue. Yeah.
So what do the log rate actually like? What do you know which environment once log rate?
So the question is exactly what's changing, and there's a couple levels to this answer. From like the most physical level at the level of bits, that 23 byte header for each row, that's storing information about the locks that are on the row. And a week after spring break, we'll talk about how it does that. The higher level thing answer though is that it's just every command inside of Postgres has a lock level that it has to acquire in order to be able to execute that command. And so we'll see later on, we'll be running insert statements and update statements and these other commands, and those will all implicitly acquire a lock, and that command will only be allowed to proceed if the table has appropriate locks on it, or and the reason that those locks are needed is to ensure the data consistency and the isolation and those other properties. So it's very rare in practice that you would want to use an explicit lock like this, but there's implicit locks that we need to understand how those are going to make different programs slow down and stop their execution. And so in order to understand those implicit locks, we're going over the explicit locks now.
If you, like run a command that requires a specific lock in the first session, and for committee, run a command in the second session that requires like a shared lock, void lock.
Yeah, so let's make sure we're not in any transactions in either situation here. And up here, so start a transaction, lock table T in exclusive mode. So exclusive mode is called exclusive because it blocks with everything. And so if we just lock this other one in exclusive mode, oops, I'm not in a transaction, begin in the transaction, lock it like this. And now this table, this process over here can't make any progress in what it's doing until this process up here finishes its transaction. I don't know if that's answering your question.
I meant like, did you say like that some commands is this lock is right? Like,
So let's pause the question for like, I don't know, 2 more pages. Yeah. Good question, but we'll wait on it. Any other questions at this point? Okay. At this point, like, so just connecting to the SQL standard and other databases, everything about isolation levels and the basic transactions is part of the SQL standard and implemented everywhere. The SQL standard also includes the lock commands, but what the actual lock levels are is up to the database implementation. And so these lock levels are what Postgres implements. If you're in Oracle or MySQL, SQLite, anything else, there will be different lock levels that they have implemented for their various internal technical reasons. But there will always be just some sort of table like this that you can look at to see what blocks with what other things. And then again, the reason for caring about the explicit locks is so that when we get to this problem 21 down here, these implicit locks, we know how things are going to interact with each other. These first section on the implicit locks, problem 21, we are acquiring an explicit lock over here, and we're going to see how that relates to an implicit lock on the right-hand side. So I'm not even going to rerun the create table command. I'll just make sure that we're in a new transaction here. So let's do begin on the left-hand side, and then lock table T in access exclusive mode like this. Oops, and then still in a transaction over here. And so we've ran lines 1, 2, 3 so far. We have a lock on the table T right here, and we want to try to insert values into our table. So insert into T values 5 like this, and you can see that it's locking down here, or that it's blocking down here. Blocking is the verb that happens when you're not getting control flow back. Locking is the verb that causes that control flow to not be given up. I always get, they rhyme with each other, so I always get them tongue-tied. How do we know that this is going to block with the access exclusive up here? The fact that it says access exclusive suggests that it's going to block with a lot of things, that only this transaction will have access to the table. But the way that we actually know is that we have to first figure out what is the corresponding lock level of the insert command. And in order to do that, it's kind of hard to figure out that each one of these block levels has a little paragraph about it that describes when Postgres is going to use that block level. And you basically just have to read all of those paragraphs to figure out which one is the one that corresponds to the command that you're interested in. In this case, we're looking for the insert command, so I'll do a slash and insert here. And we can see that the commands update, delete, insert acquire this lock mode on the target table, the row exclusive lock mode. So whenever we run the insert command it is acquiring a row exclusive lock on the table before actually running the insert command. So because this line 4 right here is acquiring the row exclusive lock, and we already have an access exclusive lock, we'll go back down here to our table about what blocks. We have our row exclusive right here. That's the thing that we're trying to acquire, the lock that we are requesting. Come over here until we find access exclusive, and we see that it's blocking with access exclusive. And so that's why we're blocking. And so I haven't been annotating over things over here in a while, but I'll put the circle over here to indicate that that line is blocking because we're in the access exclusive lock over here on the left-hand side. The main thing at this point to take away is the mechanics of, if you have a command, how do you figure out what is the lock that is being requested? And you come over to the explicit locking documentation. Again, the explicit locking documentation is this bottom link right here. And then you search the explicit locking documentation for the command that you're trying to run. The command that you're trying to run will likely appear in multiple places in the file, and so you might have to search a little bit. But here it's telling us that the row exclusive lock is being acquired by insert. Each command will acquire at most one lock, and so as soon as I see that insert appears in row exclusive, I know I don't even have to look at share update exclusive or any of these other lock levels. I know they're not being acquired by the insert command. Once you know that this is the lock level that's being acquired, that it's the row exclusive, then you come down to the table and look up on the table row exclusive with the existing lock level, and that will tell you whether it blocks or doesn't block. In this case, we have an explicit lock on the left-hand side and an implicit lock on the right-hand side. Is that a question or no? What happens if we have implicit locks on both sides? So if we keep scrolling down a little bit, implicit locks to there we go. Well, yeah, I guess I didn't put any interesting commands on the left-hand side doing an implicit lock. I know later on there are those commands, but I do expect you to be able to, if you have a command over here, to figure out what is the implicit lock level. Let's go to problem 32 right here. Problem 32, we do have an implicit command or an insert command over here, an insert and an insert. Both of these will be acquiring the row exclusive lock level, the row exclusive lock level for both of these. And so this is line 3 right here is equivalent to just having a explicit lock on row exclusive. And so in order to figure out whether line 5 over here will block or not block, we'll come over here, row exclusive, find row exclusive column, see that there's no X right here, so it should not block. So I should be able to do both of these sessions without blocking at all. Let's go ahead and test that out. Let's make sure I'm not in a transaction, roll back, make sure I'm not in a transaction, okay. And then we'll begin, insert into T values 5 on the left-hand side. So just run line 3 over here, insert into T values 5 is this over here. This did acquire a row exclusive lock. And now on line 5 over here on the right-hand side, insert into T values 6, insert into T values 6 over here. This is also going to acquire a row exclusive lock, and it works just fine because the row exclusive does not interact with each other. So it's just fine to, on these particular tables, this particular table, to insert 2 commands, and they won't block each other. Commit up here, commit down here, and everything is good. I guess I didn't put this inside of a transaction. So the commit's giving me this warning. But the important thing is that neither one of them blocked. They both updated the table. Any questions? Yes.
So say there's an implicit lock for insert, does that last until the end of the transaction, or is it just until insert gets on?
Great question. Anytime you acquire a lock in Postgres, it lasts until the end of the transaction.
So if you had like in session one, if you had another statement after the insert that had a different lock, could get a block on your.
If you have so in one session down here, let's begin a transaction. Let's lock table T in exclusive mode like this. So nobody else is allowed to use table T, but I can still insert into T values 5 right here. This is trying to acquire that row exclusive lock right here. That's an okay thing to do because it's my transaction that has this lock acquired. It's just a different transaction is not allowed to acquire the row exclusive lock. A different transaction will block, but my transaction will not block. Good question. Any other questions? Okay, we'll do just one last example problem, getting into a very exciting topic called deadlocks when no program can make progress. And that will be, we'll just introduce that real quick for today, and then we will well, maybe we're having to scroll down too far for that. So I don't want to jump ahead for that. And we're close enough to the end of class that we'll just call it for today, and we'll pick up here on Wednesday after the quiz. If anybody has any questions about this or anything else, happy to stick around. I have office hours now to help you out, but that's the end of class.